Hello and welcome. Introduction. Now, in my previous videos, I have demonstrated how to display the analog voltage from the TM4C LaunchPad board onto the serial terminal using assembly language with the floating point unit or the FPU. Now, in this video, I'll show you how to display the analog voltage from the TM4C LaunchPad board onto a serial terminal using the C language. I will also make a comparison of the assembly version and the C version. Hardware setup. The hardware setup for this video is exactly the same as the one I used in my last video. That is, I'm referring to video 100. I've left the link to that video in the description. Now, I'm repeating the hardware setup here for clarity. Now, so here is the schematic. This is the 220 ohm resistor. The purpose of it is to limit the current. So to limit the current when the middle pin or the spindle of the pot is turned towards the 3.3 volts reference voltage. So when it reaches this maximum, it doesn't get shorted out because of this 220 ohm resistor. All right, so the one end of the 220 ohm resistor is connected to 3.3 volts. As mentioned, this is the reference voltage. And the other end of the resistor is connected to the 1K potential meter. And the middle pin or terminal of the potential meter is connected to PE3 of the LaunchPad board. Of the 3.3 volts, by the way, is also from the LaunchPad board, and the other end of the potential meter is connected to ground of the LaunchPad board. Here is the LaunchPad board, and I'm going to zoom in on here and also to repeat the schematic. All right, so this is the zoom in version of the board with the pins labeled, and then this is the I repeated the schematic here for clarity purposes. So as mentioned earlier, the 220 ohm resistor is connected to the 3.3 volts pin, which is here, this one here, and then the middle pin of the potentiometer is connected to PE3 of the LaunchPad board, and then the other end of the potentiometer is connected to ground of the LaunchPad board. All right, so this is the wiring diagram. Now, the LaunchPad board has to be connected to a laptop or desktop. Now, to do that, I use a USB to TTL adapter cable, as shown here. All right. And here are the connection or the wires of the cable, of the USB TTL cable. Let's zoom in on this part. All right, so the red connection or the red wire is the 5 volts. The black connection or wire is the ground. All these are referring to the USB TTL cable, adapter cable. Now the white connection here, that is TX, the transmit, and the green connection, that is RX, the receive. So the ground pin of the potentiometer, that's connected to ground pin of the TM4C series LaunchPad board, but it's also, I have also tied it to a header pin here, and then the middle pin of the potentiometer that is connected to PE3 of the LaunchPad board, but it's also connected to this header pin here. Now, as I mentioned earlier, these two header pins, I put it in so that I can measure the analog voltage from the board later on during the demonstration. The program. Complete listing. So here is the complete listing of the program. So we start off with this part here. This is the including the what you call the header files for this program, and then here I declare the functions that are being used in the program. So here we have the enable clocks, the initialize UART5, configure UART5, initialize GPIOE, configure ADC0, transmit UART5, display string, and then the delay function, and followed by these two global declaration of global variables. As we scroll down, this is the start of the main function all the way down. At the start of the main function, I have declare one variable called ADC result, following by invoking or calling these subroutines, which was declared earlier up here. All right, so the first one that I invoke is the enable clocks, initialize UART5, configure the UART5, initialize GPIOE, and then configure ADC0. Then here is a while endless loop, and these instructions here. All right, now I'll go into the details of this later on. And then here I have and here basically that's the end of the main what they call function up here, or way up here. All right, so this is the main function, and starting from here we have the I have defined the enable clocks function. I define the initialize UART5 function here. Then I define the configure UART5 function, followed by the initialize GPIOE function. Then have the configure ADC0 function. And then I define here the transmit UART5 function, followed by the display string function, and then finally the delay function. So this is the complete listing of the program, and I'll be going into the details in a few moments. The program explanation. Okay, so let's start by looking at this include TM4C123G 6pm.h, and then also include stdio.h. Now the stdio.h is a standard input-output header file used for standard operation like formatting strings. And this TM4C123G 6pm.h header file defines the register macros and the memory map addresses for the TM4C123GH6PM microcontroller, which enables the low-level hardware access. Now, I've covered this header file in my previous video. If you're new to the channel and you're not familiar with this, please refer to my previous video, that is video number 98. Now, I've included the link to that video in the description of this video. I will, however, briefly mention it here for clarity purposes. Okay, so here is the Kyle Microvision IDE, and this is the C code that I'll be using in this video. Now, if you look at this panel here, you'll find that the TM4C123GH6PM .h header file in either the source group or under the device. All right, if you click on either one of them, you will be brought to this file. And if you scroll down the file, you'll find the definition of the type def structure or struct for GPIO-A. And then if you scroll further down, you'll find the structure for ADC 0. Now, I'm just highlighting this for clarity purposes. So this is the .h, the TM4C123 GH6PM.h header file. Okay, let's go back to the code. And having mentioned the header files, then this is followed by the declaration of the functions that are used in the video. So the first one is enable clocks, followed by initialize UART5, then configure UART5, initialize GPIO-E, configure ADC0, transmit UART5, display string, and then delay. And then I've declared two global variables. The first one is text of the type char. Next one is voltage of the type float. Here is the main function. Now, here I declare a variable called ADC result of the type unsigned int. And here I call or invoke these functions. They are enable clocks, initialize UART5, configure UART5, initialize GPIO-E, and configure ADC0. And this is the while infinite loop. All right. And here I've covered these instructions or statements in detail in my previous video. And if you are new to the channel, please refer to the video link in the description. Here, I will just mention the purpose of each of these statements, starting with this ADC 0 arrow PSSI statement. Basically, this statement here will start the conversion for sample sequencer 3, while this one, the while statement here, wait till the ADC conversion is complete, and then assign whatever conversion result or retrieve the conversion result from the SS3 FIFO and assign that to ADC result. which was declared here. And then this statement here will clear the interrupt flag for the sample sequencer 3. Now, the purpose of this clearing the interrupt flag is to enable the next conversion to start. And here, the ADC result is multiplied by this scaling factor and assign the result to voltage. Again, here voltage is a global variable which was declared earlier. Now, sprint F statement here, basically this function formats a string, which is this string here, and then stores it in the text character array text. Now, this was declared at the beginning of the program. All right, this was declared at the beginning of the program, and the formatted string, all right, includes this string here and also the value of this voltage. All right, so the text array includes not only the string but also the voltage value. And then display string function here will basically display whatever is stored in the text array, which is the string here plus the voltage value, and then followed by a delay. Okay, so this function here, this enable clocks function, is responsible for enabling the system clocks for different peripherals of the TM4C123G 6PM microcontroller. Now, we need to do this because before we can start using the UART5, GPIO, and ADC, we need to enable the respective clocks. So this statement here will enable the UART5 clock. Then here, this statement here will enable the GPIO clock. And then this statement here will enable the ADC0 clock. Right. The utilize UART5 function. Now, this function is responsible for configuring and initializing the UART5 module of the microcontroller for the purpose of serial communication. All right, so let's start off with the delay. So here is a short delay to allow the clock to stabilize before configuring the UART5, the UART module. So the first statement here, disable the UART5 module. Then this statement here will set the integer baud rate. And then this next statement here will set the fractional baud rate. And this statement here will select the system clock. And this statement here will set what they call configure the UART line control, and 60 hexa. Basically, that sets the 8-bit data length, no parity, and no FIFO, first in, first out. And then this statement here, basically, that will enable the UART5 module. Here we disable it, here we enable it. Now, a lot of the details of these statements here, the instructions here, they are being covered in my previous video. So if you are not familiar with it, if you are new to this, please check out the video link in the description. Hey, so this is the config UART5 function, and basically this function configures the GPIO port E, that is PE4 and PE5 for UART5 communication. Now these pins, all right, PE4, that is port E bit 4 and port E bit 5, PE5, needs to be set up correctly so that they can function as transmit and receive lines for the UART5. All right, so the first statement here enables PE4 and PE5 as digital function. And then the next statement here basically enable the alternate function for PE4 and PE5. Remember, GPIO-E, or general purpose input output for port E, they basically can function as input output and function as UART and other functions. So we need to enable the alternate function, all right, instead of the general purpose input output function. So the next statement here basically disable the analog function, and then this instruction here basically it will set up port PE4 and PE5 for UART operation. Right, so this function here is the initialize GPIO-E, that is a GPIO for port E. So we need to configure, basically this will configure PE3 as an analog input for channel for the ADC 0 channel. Now, so the first instruction here basically enable the alternate function. This instruction here will disable the digital function, and this instruction here will enable the analog function. Okay, so this function, the configure ADC 0 function, configures the ADC 0, or the analog to digital converter 0, of the TM4C123G H6PM microcontroller to use the sample sequencer 3 SS3 for analog input conversion. So the first statement here, or instruction, basically disable the sample sequencer 3 SS3 before configuration. Then the next instruction or statement here basically is a software triggered conversion. Then this statement here basically sets channel 0 as the input source for SS3 and gets the input from channel 0. Now this one here configures SS3 to take a single sample. And then the final statement in this group here basically enables the ADC 0 sequencer 3. And then this function here, the transmit UART5, all right, sends a single character. That the purpose of this instructions here is to send a single character over UART5 module. And this statement here or instruction here basically waits for the UART5 transmit FIFO buffer, the first in, first out buffer, waits for it to be empty before sending the data. then this instruction here basically writes the character or the data into the UART5 data register. And then this basically initiates the transmission over the UART5TX or PE4 pin. Now this function, as the name suggests, sends an entire string over the UART5 by invoking this function, which is this one here, for each character. So for each character, invokes this to send the character. And then finally, we have the delay function. As the name tells us, that basically this generates a software delay. Demonstration. Okay, so I have started my Kyle Microvision IDE, and I've uploaded the code. So just let me briefly go through the code. I'm not going to go into the details as we have discussed this earlier. So here are the include directives. Then I declare the functions here, and also declare these two global variables, text, which is an array, and then voltage. And then the main function starts here. The int main, it ends here, and then if I go down further down here, I have my enable clocks function defined, and then the initialize UART5 function defined. Then I have configure UART5, initialize GPIOE, and then I have the configure ADC0 function, then the transmit UART5 function, and display string function here, and then the the delay function here. Right. So let me just go back up here. I go to project, click on that, build target, successful, 0 errors, 0 warnings. Let me now just quickly show you the physical setup. Alright, so here's my physical setup. Let me just turn this thing around. Alright, so this is my potentiometer, which I'll be using it in a moment. Now, let me just go back, swing it to this side. Now, I will download the code to the board. This camera will go off for a little while, but not to worry, it's still be there. So I click on download. And erase done, programming done, verify, okay. So let me bring up the board again. Okay, now I need to bring up the Tera term, which is the serial terminal here. Let me just stretch it a little bit. Yeah, okay. Now, if I press the reset button here, alright, so the output is being displayed onto the serial terminal. Alright, you can see the variation of the output here. Alright, so let me just go to the other camera, if I can bring it up here. Alright. So let me just see if I can move this around. Alright. So let me just adjust the range of the multimeter. Right, okay. So what I'm going to attempt to do is I'm going to attempt to measure the output. All right, somewhere around here. I'm sorry I don't have a zoom here. So I'm going to try to measure the output. Look up for the multimeter reading. All right, so I'm getting 1.6, 1.7 is fluctuating, which is basically more or less of what is being displayed on the serial terminal. Let me see if I can. All right, so it's steady. Oh no, it's all right. So that's it for now. Compare and contrast. Okay, so we're back in the Carmichael Vision IDE. At this point, what I'd like to do is to compare this C version of the software of the program with the assembly version, which I did in the last, in my previous video. So let me just go back to the C version first. The first thing to notice is the readability. Now, if you look at the C version, the statements of the instructions are written in English-like instructions, which is easier to read and understand. Whereas if I go over to the assembly version, which is this one here, you'll find that it's a lot harder to read and understand unless you have an understanding of the instruction set with instructions like LDR, MOV, STR. So that's the first thing. The other thing is that is most obvious is the length of the program. As you can see, both the version of the program achieve the same outcome, that is to display the voltage value from the ADC module of the TM4C series board. So let's go back to the length. So if you look at the length of the C program, it's only 107 lines of statement or code. Well, of course, including the space. But if you go to the assembly version, it's a lot longer. In fact, it stretches all the way down to nearly, it's to 394 lines of code. And to display, for example, the message, you have to define the strings and buffers to do that. And you need to convert the voltage value to ASCII value, and you need to format the voltage strings. And then if you go further up here, we need to convert the ADC value to voltage value using floating point unit, the FPU. Or else this is hidden in the C version. So that is the other point that I'm trying to make. Now, let me just close this. Let me just try to build the project. I'll show you why I want to do that. Let's build this project or compile it. Okay, so that's not what I'm hoping for. Let me just rebuild the target. Right. Let me just bring it up here. I just want to point out, let me just I want to just point out the code size of the C program, and we are getting 8,640 bytes of code for the C version. Hey, so let's take a look at the assembly version. Now I'll go to project and I'm going to do a rebuild all targets. Right, so let me just move this up. Let me zoom in here. And the code size is 1012, 1012. Now, the thing is, although the length of this assembly version is about I think it's 394, the code size is only 1012, 1012. Where else if I just go to the C version, right? That is only the length of the C version is 107 lines of code, and the code size was 8, as we've seen earlier, it's 8,640, 8640. Okay, so we're back in the Kyle Microvision IDE. This is the C program that we've seen earlier. So what I'm going to do is I'm going to rebuild the target files. All right, and I'm going to download the file into the board. All right. All right, so this will go off for a little while, but you bring it back up again. So I'm going to download the file, the file onto the board. All right, let's bring this back up. Now the programming is done, it's successful. So now what I'm going to do is I have set this pot, the potentiometer, to this position. All right, I'm going to fix it at this position, and I'm going to now bring in the Term terminal. I think it's up here. Right, it's here. And I'm going to press the reset button. All right, so it's showing these values. So let me just measure the output like before. So we will, all right, so, oh yeah, I need to bring the other camera back up here. Where is it? Yeah, okay, right. So let's measure the output. All right, it's 1.78 on the multimeter. It's reading 1.755855 on the terminal, which is not too bad. Right. Now, that's it for the C version. All right. I'm going to now upload the machine code version or the assembly version of the code and run it and look at and then compare the two outputs. Okay, so here we are again. So we have the Kyle Microvision IDE running, and this time I've got the assembly version of the code up here. Just scroll down. Let me just scroll back up. All right. Now, let me just go to project, build the code. So build target. So we're okay. Let me just bring up the camera. All right, and then let me download the code. This one will go off for a while. Bring it. So programming done, verify OK. All right. So I've kept this potentiometer in the same position as before, as with the C version. Let me just bring up the other camera where we can see the multimeter, and then now the serial terminal. Let me clear this. Clear screen. All right. Now I'm going to press the reset button and watch out for this serial terminal. All right. So more or less reading the same output, displaying the same output. Let's measure the output with the multimeter. And we have 1.78, 1.77, right? More or less the same as before. And the serial terminal is displaying 1.4. Earlier part we have 1.72 and so on. All right, so that's it for the assembly version. Observations. Let's take a look at this table. Now, in terms of readability, if you recall, in the assembly version, it is harder to read, and for the C language version, it's easier to read. Now, code size, we have seen, although the assembly language version is much longer, the code size is smaller compared to the C language, where the C language, the code length is much shorter, but the code generated is much larger. Now, portability, as observed in my previous video, the assembly language is not so portable because it's tied in specifically to the microcontroller or CPU use. Now, in our case, it's the TM4C123G 6PM. So the assembly version program that is written is specifically for that microcontroller only. Whereas C is a much portable option where you can port the same program over to another microcontroller or microprocessor with some changes. Now, development time, although it's not so obvious from the example that we see, I can testify that it is a lot harder and slower with assembly language, and it's a lot shorter development time using the C language. Okay, so that's it for this video. I hope you have found it useful. Thank you for watching, and I'll see you in the next video. Bye!